In this lecture, we're going to take a look at two topics. One is gas pressure, which we're going to use a lot later on in this unit. And then we're also going to talk briefly about the properties of liquids. In this class, we're not going to investigate liquids very much because the properties of liquids are specific to the individual liquid or to groups of kinds of liquids. And it's a fairly deep study. We're going to focus on gases much more because they're easier to understand and the rules that they follow are more or less universal. To talk about gas pressure, first of all, we should probably define what pressure is. The physics way of defining pressure is the ratio of the force applied to the area over which it's applied. The standard unit in the SI system is called the Pascal, and it is the standard measure of force, which is newtons, divided by the standard measure of area, which is square meters. A newton isn't a huge amount of force, and a square meter is a fairly large amount of area. So a Pascal turns out to be a fairly small number, but it is the SI standard. One way of thinking about the pressure that the atmosphere exerts on the Earth is by thinking about a column of air that is 1 square meter on its base, and it goes all the way up to the top of the atmosphere. That would have a big enough weight that it would exert 101,325 newtons of force. That would be the weight of that 1 square meter column of air. So that means that the Earth's atmosphere has a pressure of 101,325 newtons over that square meter, or that means 101,325 pascals. Just for reference, in the US system, 1 square inch of atmosphere, so we're talking about a square like literally this big, would weigh 14.7 pounds. Pounds per square inch is what we call PSIs. We use that fairly commonly in the United States. Another way that we can understand pressure is by the use of something called a barometer. So this is how a barometer works. This is the basic schematic for it. You have a bowl full of mercury. You fill up a long skinny tube with mercury, plug the end, flip it upside down, put the end of the tube under mercury, and then take your finger away. So what happens is, because mercury is heavy, it's going to start to sink down into the bowl. But because there's air pressure pushing down on the bowl, that's going to cause a balance to occur, and the mercury will only go down so far before it reaches a balance. Then you measure how high it is. And if you measure that in millimeters, you kind of have a pressure unit. When the pressure gets higher in the atmosphere, that's going to force a taller column of mercury to rise into the tube. And if the pressure drops in the atmosphere, that's going to allow the mercury column to sink further into the bowl. So the pressure units that come from the barometer, I've already mentioned the millimeter of mercury. That's renamed the torr after Evangelista Torricelli, who is the person who invented this measurement tool. If you, on average, at the surface of the Earth, measure the height of that column, it's going to average out to 760 millimeters. And so 760 millimeters has been called 1 atmosphere of pressure. That's another pressure unit that arises from the barometer. If you were to measure that in inches instead of millimeters, you would find out that an atmosphere is 29.9 inches of mercury. And then to relate that to our physics pressure units, 1 atmosphere, remember, that's 101,325 pascals. That's the weight of the atmosphere in newtons per square meter. Because a pascal is so small, we usually use kilopascals, so it's 101.325 kilopascals. 14 pounds per square inch is an atmosphere. And then there's another unit called a bar. And a bar is 100,000 pascals. Since 101,325 pascals is an atmosphere, a bar is close to, but not exactly, 1 atmosphere. Millibars are commonly used to measure pressures and vacuums as well. And a millibar is 100 pascals. So that means an atmosphere is 1,013.25 millibars if you do all the conversions. You don't have to memorize any of this stuff. You will probably come to know that 760 torrs is an atmosphere just by using it over and over again. But that gives you an idea of how pressure is measured. If you're trying to measure something other than the atmospheric pressure, you can use a manometer. So let's say you have a gas in here, in this tube, and it's connected up to this U-shaped tube that has mercury in the bottom of it. If the pressure in the atmosphere and the pressure of the gas are exactly the same, well, then those two levels of mercury are going to be the same. But if the pressure of the gas is bigger than the pressure of the atmosphere, then the pressure of the gas is going to push the mercury column over onto the right side, and you'll be able to measure the difference between these two sides in millimeters of mercury, because it's mercury in the tube. So that would mean, in this case, that the pressure of the gas is equal to the pressure of the atmosphere plus however much difference you have between the two heights, because the pressure of the gas is bigger than the atmospheric pressure. If the pressure of the gas is smaller than the atmospheric pressure, well, then the column is going to get pushed up on the gas side of the column. And in this case, the pressure of the gas, because it's less than the atmospheric pressure, would be whatever the atmospheric pressure is minus that height differential. Here are some other pressure sensors that don't involve using a toxic liquid. This is a bellows type pressure sensor. So you have, this is open to the atmosphere pushes up in here, and it forces this sealed up little bellows to get smaller when the pressure is bigger or larger when the pressure is smaller, and that's attached to this little mechanism that makes a needle spin on a dial. And this is a diaphragm type. So here's the open atmosphere. There's a welded shut diaphragm. So the atmospheric pressure is going to cause that diaphragm to flex up and down depending on how hard it's being pushed, and then that's attached to a little mechanism that spins a dial. Now both bellows and diaphragm type pressure sensors can be made pretty small, especially the diaphragm types can be made very small. And also, instead of using a mechanism with a dial, these can be attached to sensors that can detect these movements and read out on a digital display, and that's how that's commonly done nowadays. Talking about liquids now, liquids, one of the things that makes them different than gases is that they're incompressible. If you squish a gas into a smaller space by applying some pressure, it will readily change its volume. But liquids don't do that. If you put pressure on them, they don't change their volume very much at all. And the reason for that is because gases have a lot of empty space in between the particles. And so when you squish them, they have a place to go. But in liquids, the particles are already quite dense. They're very close to each other, and there's just not very much room. So when you try to push on them, there's just no place for them to go, and the volume just stays pretty much the same. Here's another property of liquids. The rate of diffusion in liquids is lower than it is in gases. And again, it's because of the particle spacing. If this is a particle of, say, perfume or something, and it's going through the air, it's going to move in long sweeps before it collides with any gas particles, because the gas particles are far apart. But if you're trying to make that same substance move through a liquid, it's going to collide with particles much more often because they're much closer together, and it's just going to take a lot longer to get through the same amount of space if that space is filled with a liquid. Another property of liquids is that they exhibit something called surface tension. You can see this exemplified here by this water bug or water beetle. They can walk on the surface tension of water. You can, if you look at the insect's feet, it looks like they're actually on like a mattress or something like that. There's a tension on the surface of the water that they're taking advantage of when they walk on that water. Here's another place that you see that. You can, if you're very careful, fill a glass up beyond the top of the glass, and there's some tension that holds the liquid all in there. Here's why that happens, is because the particles on the surface are under different forces than the particles in the middle. Here's a water particle in the middle. It's attracted to all water particles all around it. So the forces on that particle and all the particles in the middle are pretty even. But if you look at a particle that's on the surface, there are no particles out here on the outside of the liquid to attract it. So its net attraction is towards the inside of the droplet, and so that's the surface tension. It's the fact that the particles on the outside are pulled towards the inside and the other particles are not. One place where you see liquids exhibiting surface tension would be a droplet on top of a fabric. So if you have a drop of water on some cloth and you look at it close up, these are like the little individual fibers, and water molecules, because of surface tension here and here and here, that water can't sink down into the fabric. And that's a problem if you're trying to wash the fabric, because you want to be able to get the dirt that's in between the fibers out of there. So you add something called a surfactant, or a surface acting agent, and these surfactants are able to break up the surface tension, and that allows the water to spread out more and also to penetrate into those fibers. And so that's why we put detergents in our washing machines, so that we can get in between the fibers and get the dirt out. Liquids exhibit surface wetting. The surface tension that we were talking about is due to attractions of the liquid particles for other particles of that liquid. Sometimes that's called cohesion. Surface wetting is due to the attractions of the liquid particles for surface particles, for the particles of the surface that they're sitting on, and that's called adhesion. Here's an example of surface wetting being greater or lesser depending on the surface. So you may have seen this before if you've washed a car or just gone through a car wash. Before the car is waxed, there is a lot of surface wetting because the water particles are attracted to particles in the paint of the car. But once you put a coating of wax on top of the car, then the water doesn't stick to it and it just runs off very quickly because it's not attracted to the wax particles as much as it is attracted to the paint particles. Another place we see surface wetting is in capillary attraction. Liquids will actually climb up or down inside of skinny tubes called capillary tubes because of the fact that they're attracted to the particles that the tube is made of. Here's another little surface wetting video that I made on a waxed and an unwaxed part of a ski base. So I put a drop of water on a part of my ski that was not waxed and then just kind of squished it around with the pipette. And you can see that it spreads out pretty readily. Not completely, but you can disrupt that particle and make it into a bunch of little particles. Now I move to a part of the ski that is waxed and put my droplet on there. And as I try to move that droplet around, it actually stays together because it's not as attracted to the waxed part of the ski as it was to the part that was not waxed. The final factor that we'll talk about with liquids is something called viscosity. Viscosity is the measure of how well a liquid resists flowing. Viscosity depends on three factors. One of them is the intermolecular forces that exist between the particles of the liquid. The higher these intermolecular forces are, the more viscous the liquid is. And when we think about viscosity, we think about something that's like thick, that doesn't flow very well, something that's very viscous, like maple syrup or something like that. Another thing it depends on is the complexity of the particle. Particles that are long and stringy, have a lot of complexity, are going to tend to be more viscous. And we can see some examples here, like water has high intermolecular forces but is not very complex. Its viscosity in this megapascals seconds unit is 0.890. In the same unit, here's ethylene glycol, which does hydrogen bonding just like water, strong IMFs, but it's a much more complicated molecule and its viscosity is much higher. Octane is similar in complexity to ethylene glycol, but it only has relatively weak intermolecular forces, and so its viscosity is not that high. And then the final thing that viscosity depends on is the temperature. You probably all have noticed that if it's really cold out, lots of liquids don't flow very well, and if it's warm out, those same liquids will flow quite nicely. Like there's a whole saying that used to be common about molasses. That when you're trying to describe someone or some process being slow, you would say it's slower than molasses in January. When it's cold, the viscosity of molasses is very high and it barely flows at all. And when it's warm out, or if you heat it up, the molasses becomes quite fluid and will flow quite readily.